Hey everybody, Hipster Username here. In a departure from our normal tutorial style where I just go through the app, I want to talk through a couple of fundamentals that will help you understand the basics of how this process works and how you can make the most of the advanced tooling available in InvokeAI. In this video, we'll cover how diffusion works, how these models are trained on images, and how they learn to generate new content using machine learning. This won't be overly technical, and I'll do my best to make sure that it's easily understandable to the average user. But by understanding these processes, you'll be able to create even better content using the tool. So let's dig in. To understand diffusion and how it's used in creating new content, we have to understand how machines are taught on the images in the training set. During the training process, machines are given an image with a description. So, for example, a cat in front of a red chair. And they observe the image as it's transformed by adding noise to the image, to the point where it becomes completely incomprehensible. It's just noise. And then the machines practice generating that image, starting from the noise and working backwards, trying to get as close to the original image as possible. By doing this over and over again, machines get really, really good at generating images from noise using a text description. And we refer to this process as denoising, taking a noise input and turning it into an image. As I mentioned before, when a model is being trained, an image and a text description are passed in, and the machine observes the latent image turned into noise, and then the model is tasked with recreating that image from the resulting noise. By doing this on the broad range of training data, what ends up happening is that the model develops an understanding of the individual terms in each of the pictures. And in this way, it begins to look a lot like a dictionary, with entries for each of the words and definitions for what the model understands that word to mean in an image. When we think about how we're using these models to develop new pictures, we're passing in a text prompt. It is being interpreted by the model's perspective on what those words mean, and it is transforming noise into the resulting image. The denoising process does not happen all at once. It happens over a series of steps called the denoising steps. And those are organized and orchestrated by a scheduler, which determines how it will perform those steps, how those will be arranged over the denoising timeline, and how the noise will be interpreted into the resulting image. When using diffusion models, it's important to understand how the prompt and the model interact. A number of popular image generation services like DALL-E and Midjourney manipulate your prompt for you to help you get to a resulting image that is aesthetically pleasing. However, what that ultimately does is restricts your ability to control what is being used to prompt the model. Invoke, along with many other stable diffusion UIs, do not manipulate your prompt before it's passed to the model. And so it's important to really understand how to get the subject and style that you're looking for from the system. This is a useful framework that'll help you develop a strong prompt, but I definitely recommend taking a look at the wide range of community content that can help you learn specific terms and prompt structures to get the resulting images that you're looking for. In this case, I've created a prompt with a subject and a style that is composed of a category, quality modifiers, and general aesthetic or composition terms. And we can see a couple of the images that this prompt generates. The important thing to understand with your prompt is that if you use the same settings and the same noise, you'll generally get the same picture. And what that means is that if we want to experiment by adding new terms or adding negative prompts to the system, which effectively tell the model what we don't want to see, we can develop a stronger understanding of what individual terms do to our images. In this case, I've added the term joyful, and I've added a negative prompt saying that we don't want anything gloomy or anything mysterious. And as a result, the images are a little bit brighter and more celebratory in nature. And if we compare the original images with the new images, if we were going for a much happier aesthetic, the new images definitely fit to that better. Again, the reason that there are structural similarities between the images that we generated is because we kept the noise the same. In diffusion, this is controlled by a number known as the seed. If you use the same seed, the same noise will be generated, and you'll be able to reproduce or experiment with your images. When we think about the denoising timeline, we can think about a countdown from 1 to 0. And this is an important concept to understand when we talk about things like image to image. Image to image allows us to pass in an additional prompt into the denoising process, but that prompt, rather than being a text-based prompt, is an image prompt or an initial image. The process of image to image merges our noise and the initial image into a noised image that the denoising process takes place over. So if you view this on a timeline, our original prompt of a photo of a sunflower on a car would be produced over a series of steps to generate our original picture. This doesn't have any type of image prompt in it. It's just the standard denoising process. However, if we add in an image prompt, we're presented with a new option called denoising strength. And what denoising strength determines is how much noise to leave in the noised image and how many steps are left in the denoising process to get to the resulting image. Put another way, the denoising strength determines how much like the original image prompt you're providing the resulting image should look like. If you have a denoising strength that is high, you'll be providing it earlier in the denoising process. The machine learning model will have more time and more noise to work with in order to generate new content in the image. If the denoising strength is low, on the other hand, which means more on the right side of this chart, we would be giving the model less time and less noise to generate the new image, meaning that it'll look a lot closer to our image prompt. Just as an example, I've used the same seed, prompt, and image prompt to generate the 4 images below. When we have a very high denoising strength, which means we're injecting the image early on in the process, there's a lot of noise, and the machine learning model generates something that looks quite a bit different from our input. However, the lower we get on the denoising strength, the closer and closer our image prompt looks to our resulting image. I cannot express how important it is to understand this concept because it's used in many of the advanced techniques like in-painting and out-painting, as well as control adapters, which I'll talk about next. With the release of control adapters like ControlNet, we now have the ability to condition the denoising process with additional information like structure or depth or style, and all of these dramatically impact the denoising process. Each control adapter has a setting that allows you to define at what point in the denoising process the conditioning begins and at what point it ends. I'll jump into Invoke in just a second to show you how this works. But an important thing to understand is that control adapters applied early to the generation process will have a much bigger impact on the general structure and composition of the image, and control adapters that are applied at the end of the generation process will more so impact the specific fine details of the image as it's finishing out the denoising process. So let's see what happens when we add a control adapter to this robot generation that I've got. So you'll notice that I have a cute alien robot prompt that I've already created, and I'm using the same noise to generate this picture. I've turned the random setting off, but I'll leave everything else the same. And what I'll do in my control adapters section is enable my ControlNet and use the soft edge model. I've already passed in a previous generation that I'm using as a soft edge inspiration. And what the control adapter is doing is converting this into a pre-processed image that it can then use as conditioning information during the denoising process. When I generate this image, it'll apply itself to the denoising process based on the begin and end step percentage that I have set. So for this generation, I'll go ahead and have it generate through the entire denoising process. What that'll do is pass in this control adapter to condition the denoising and define both structure and detail of the resulting image. So let's give that a go. And what you'll see is that it generated a new image that maps to a lot of the soft edges that were identified in the pre-processing image. You'll even notice that some of the quirky lines here on the face have been interpreted as cracks in this robot's armor. So if we take the instep percentage down to, let's say, 60%, We're using a lot less of this control adapter in the final steps of the denoising process where a lot of the detail is added. Let's see what that gets us. What we see is that a lot of the structure from the control adapter is in the resulting image, but some of the weirder details, like the cracks in the armor, have actually been reinterpreted into something a little bit more coherent. We've given more flexibility to the machine learning model to interpret the image and finish that image out without the conditioning information being applied. Removing the control adapters from the final range of steps in the denoising process can give you a little bit more flexibility and freedom, something that you can play with to see how to get the image that you're looking for. Now, if we do the same thing to the beginning steps, let's say remove the first 25% of steps, we're actually not providing the control adapter conditioning to the initial composition of the image. Now, typically, this is probably not advisable unless you know what you're doing, and we'll see why in a moment. This is going to have a big impact on the overall composition of the image because it's using the original seed and the original image structure early on, then providing this control adapter on top of it towards the end, which might not really map to the structure or the composition that it's been generating. Let's see what happens. You can definitely see this has some weird problems with it. And during the early part of that generation cycle, you could see that it was starting to generate this composition of our original image. And so that abrupt change now means that we've got highlights and shadows in areas that don't really make sense with the control adapter conditioning we passed in, and results in a lower quality image than we probably would want. Now, what you can do is duplicate a control adapter, and we can then have maybe more flexibility provided in the middle of the generation. So we'll start the generation and allow the structure to be defined by our conditioning. We'll give it a lot of freedom in the middle here, and then we'll finish off the image with some conditioning. And let's see how that works for us. Because we only controlled the denoising process for the first 25%, a lot of those early structural steps weren't conditioned, and the resulting image is pretty significantly different. It's a lot higher quality than when we didn't provide any of that early conditioning at all. So if we increase that to maybe 55% and we're giving more freedom in the middle, we'll likely find an image that's closer to our original control adapter image. As you can see, understanding how your text prompts, image prompts, and control adapters are used during the denoising timeline gives you a much better understanding of how to structure what you're passing into the system to get an output that aligns with your creative vision and needs. I hope this was a helpful introduction to the fundamentals of diffusion, and I encourage you to give me feedback. Was this too technical? Was it not technical enough? Was there more that you wanted to learn that we didn't cover? Whatever it is, let us know. We've got more content coming to help you better understand and leverage all of the advanced technologies that are getting incorporated in Invoke. Until then, happy denoising.